Yeah, thank you to the organizers for the invitation to speak here. This has been a really excellent conference. I've really enjoyed all the talks, so really happy to have this opportunity. And yes, I'm going to be talking about obstructing cosmetic crossing changes. So first of all, we're talking about classical knots, oriented knots in the 3-sphere, and a crossing change is exactly what you would think. If we are thinking about a diagram, we can just flip a crossing. It's also useful to think about this disk. Let me try this. It's also useful to think about this disk, which we will call a crossing disk, which hopefully the picture kind of makes it clear. We can note that the knot has algebraic intersection number 0 with the disk. So doing a crossing change, if you want to think about it more topologically, is the same as doing plus or minus 1 surgery on the boundary of that disk. So a crossing change is cosmetic, as you would expect, if it doesn't change the isotopy type of the knot. And the cosmetic crossing conjecture, due to Xiao-Song Lin, posits that only a nugatory crossing change can be cosmetic. So when we say a nugatory crossing change, we mean something that looks like this. So if you can kind of cap off that crossing disk with another disk disjoint from the knot, then you can think about doing a crossing change as you're just twisting like that, and clearly that doesn't change the isotopy type of the knot. So the conjecture says this is the only way that this can happen. Just a bit of motivation and background. Well, first of all, I think it's fun. That's my personal motivation. But I also think it's a nice idea that every crossing in a knot diagram, unless it's kind of trivial, contains some essential topological information. And again, if you want to think about it more in the context of 3 manifolds, we can think about this also as a special case of the cosmetic surgery conjecture, since it really is just a bit more general, looking at a knot complement and a plus or minus 1 surgery. And a little bit of background. It's verified for 2 bridge knots. I think this is the first result from maybe 92, sometime around there, due to Turiso. And then the next result is for fibered knots, due to F.E. Calfagiani. There's been a lot of work, so I'm not going to talk about all the work, but it was proven for genus 1 knots with non-trivial Alexander polynomial due to Ito building on work of Bohm, Friedel, Calfagiani, and Powell. And maybe I want to write their theorem here as a footnote. So they essentially proved that if K is a genus 1 knot and admits a non-nugatory cosmetic crossing change, then K is algebraically slice. So I won't say exactly what that means, but in particular, we can say that the Alexander polynomial of K satisfies a Fox-Milner condition, right? So it looks like FT inverse for, F is either linear or constant, since it's a genus 1 knot. So this is a very nice result. And then Ito was able to upgrade this result to actually get the conjecture for all genus 1 knots with non-trivial Alexander polynomial. And then another significant result, which I'll be talking about more, is due to Lidman and Moore, and they proved it for alternating knots with square-free determinant. In fact, their result is a bit more general than this. I kind of want to write this one as well. So it actually holds if the double-branched cover is an L space, which I'll mention again later, and it admits a non-nugatory crossing change, then I want to say each invariant factor of the first homology of the double-branched cover is square free. So again, when I'm using this notation, I'm talking about the branched double cover. Yeah. I'm not going to really talk about what an L space is. I think a lot of us know. Essentially, it's a three-manifold where the Heegard floor homology is as simple as possible, but I'll essentially be black boxing that. And there's a lot of other results. So just to shout out some other names, Josh Wang has done some really important work on this, and Claudius Sabraus, and Artem Kotelski, Liam Watson, a bunch of people have worked on this problem. Any questions at this point? Yeah, so this is a finite abelian group. So just the, yeah. Yeah, because it's a rational homology sphere. That's a good question. Thank you. So 2 results. First is that special alternating knots do not admit cosmetic crossing changes. I might sometimes admit the word non-nugatory. So if I don't say non-nugatory, it's usually implied. And then the second result, we'll talk a bit about what special alternating knots are in a second. And the second result from last year is if K admits a non-nugatory crossing change and the branch double cover of K is an L space, then the Alexander polynomial has a factor, not that it's equal to that, but it has a factor of the form ft inverse for some f such that f of -1 is not equal to plus or minus 1. And the important corollary of that is that this is a non-constant factor, right? So we know that if for the Alexander polynomial, f of 1 is always equal to plus or minus 1. So in particular, this tells you that it's a non-trivial factor. If it was otherwise, it wouldn't be a super interesting result. But I want to just put that in the context of these 2 results, right? Because it's closely related. As I mentioned, this implies that we have a square-free determinant. Since the determinant is the order of this homology group, and that result also implies that it has a square-free determinant, since the determinant is, well, here I've written it backwards. If it admits 1, it has a square factor in the determinant. So this result kind of is, you know, it's not exactly either of these 2 results, but it's a bit of it kind of brings them together in a nice way. Because here we have some kind of, you know, Fox-Milner factor, and we can also say something about the determinant being square-free. And I'll talk a bit more about why this is showing up here later on. But let me say a bit about special alternating knots. Yes. And I should note, right, it can be a bit hard to determine if the branch double cover is an L space. Not super hard. But in particular, it applies to all alternating knots. More generally, all knots with thin mod 2 reduced Kavanagh homology. So that's another way to check that condition. And it also applies to the vast majority of knots. I think all but like 4-ish knots with crossing number 10 or fewer. So for low crossing number, this is a very general condition. For high crossing number, I think probably not, but it's quite common. So a knot is alternating, first of all, if it has a diagram, you go around the diagram, you hit crossings under, over, and so on. We say that a knot is a special alternating, or more generally a link, is a special alternating link if it has an alternating diagram with an orientable checkerboard surface. So when I say checkerboard surface, I'm talking about coloring this diagram in a checkerboard way. And we can see from the pictures that here the trefoil is a special alternating knot because I've shown that the checkerboard surface is two-sided, and I don't remember what knot this is. But this is another example of a special alternating knot. I don't feel like counting the number of crossings right now. I want to say it's like 8, 15 or something. So why should we care about these? Well, first of all, it's very easy to construct special alternating knots. If you take any bipartite planar graph, you put it in the plane, you can do the medial construction, which I think is fairly clear, hopefully, from the picture. So for every vertex, we get a face. For every edge, we get a crossing. And the fact that it's bipartite exactly tells you that this checkerboard surface will be orientable, and we can furthermore do this in a way that makes the diagram alternating. So it's very easy to construct infinitely many examples of special alternating knots. So that's a nice thing about this class. Another nice thing is, they were introduced by Murasugi, used for some classical results. And Murasugi used special alternating knots to prove facts about all alternating knots, using this fact that every alternating knot is a Murasugi sum of special alternating links. So I'm not going to define that, but hopefully you can kind of see from the picture, this is showing that the figure 8 knot, which is not a special alternating knot, is a Murasugi sum of two Hopf links. So if you care about alternating knots, it's a reason to care about special alternating knots. So I'll go through the proof, and I want to kind of show how it's essentially sort of a lift of a diagrammatic argument. It's not too long, but hopefully fun. So first I want to do something easy. I want to prove that alternating link diagrams do not admit cosmetic crossing changes. So clearly this is a much weaker statement, since it's an alternating knot, has many non-alternating diagrams. But this should be, let's just do this first. There's a lot of ways to do this. I want to do this, so there's an example of a crossing change on the figure 8 knot. I want to do this in the most classical way possible. So first we'll form the Tate graph, which is that graph, same graph we used earlier. And this is a signed graph depending on the crossings interacting with the graph, how they're twisting around it. And you can see that the diagram is alternating is equivalent to saying that all of the edges of the Tate graph are positively signed or negatively signed. So I'm just kind of sketching this out, but hopefully this makes partial sense. And we can talk about a spanning tree of this graph, and we can talk about the weight of this spanning tree being the product of the signs of the edges. In particular, if this is an alternating link, we're just counting spanning trees. And it's an extremely classical fact, maybe due to Fox, I don't know, that the determinant of any knot is this signed count of spanning trees. So in particular, for an alternating knot, the determinant is just the number of spanning trees in an alternating diagram. So this is a great, old, nice fact about alternating diagrams. And we can see that if we change a sign, since we're just counting spanning trees, we're going to introduce some cancellation there. So extremely classical argument that an alternating diagram does not admit a cosmetic crossing change because it's going to change that count of spanning trees. So in particular, it's going to change the determinant, which is an invariant. So can't have that unless it's a nugatory crossing. So you can think about that. Any questions? All right. So we haven't used special here at all. In fact, we haven't used not. This could be a link. So we're just using alternating diagrams at this point. But how do we lift this to a topological argument? Well, the first step is to think about the Gordon-Litherland form. which for a special alternating knot for an orientable surface is the symmetrized Seifert pairing. But it's nice because you can define it for non-orientable surfaces. So for a Seifert surface of some knot, this is a symmetric bilinear form defined on the first homology group of this Seifert surface, and the determinant of this form is also the determinant of the knot. So this is defined. We take two curves in the surface, and then we just push one out to the unit normal bundle. So technically, we're taking the inverse image of that projection. So if it's a non-orientable surface, then the unit normal bundle will be connected. So you'll get one curve. Here it's an orientable surface, so we're getting two curves because the unit normal bundle has two components. And then you just take the linking number. So very similar to the Seifert pairing. And so in this case, if you were going to pair this with this, you would get this. We're pairing alpha with itself, and you would get 2, because that would be one link. That would be a second link of it with the push-off of itself. So Gordon and Litherland introduced this and showed that this is a symmetric bilinear form. Furthermore, it's a classical fact, certainly known to Murasugi, but Josh Green did some cool things with it, that if you have an alternating diagram, then both of the checkerboard surfaces, one of them will have a positive definite Gordon-Litherland form, and the other one will have a negative definite Gordon-Litherland form. So Josh Green kind of proved a converse to this, that this is really a defining property of alternating knots, but we're only using the easy direction here. That if you have an alternating diagram, these checkerboard surfaces are positive and negative definite surfaces. So now we can give a second proof that alternating link diagrams do not admit cosmetic crossing changes, slightly more topological. So we'll think about our checkerboard surface instead of thinking about a Tate graph, and we'll take a nice basis for the homology of that surface where everything avoids the crossing that we're switching except for just one curve that hits it in one place. And we're going to think about how our Gordon-Litherland pairing changes when we flip that crossing. And we can see that it only changes in one place, and it only changes by 2. So as long as this interior matrix has non-zero determinant, we're changing the determinant. So it's essentially the same argument, right? How do we know that this interior matrix has non-zero determinant? Because it's a definite form. And restricting to that subspace, it'll still be a definite form, right? So since A is definite, the determinant of A prime is non-zero, so the determinant here is changing. It's another proof that alternating diagrams do not admit cosmetic crossing changes. So at this point, we are surprisingly close to proving the theorem, maybe, since maybe it seems like I haven't done anything. But
A11 is 1, then A11 minus 2 is minus 1. You just change the sign.
yeah. I'd have to think about, it's fairly easy to, the reason why that can't happen, I can tell you this, I guess you need a little bit more, right? But you can argue that, I'll keep going and it'll be clear, I think. Because I think the next argument will help. But you're right, there's kind of a subtlety there. Yeah. So we can now sketch the theorem, right? So we're going to leave diagrams behind. We're just working topologically. And we're just talking about, we can talk about now like plus or minus 1 surgery on a crossing disk instead of thinking about a diagram. And the first thing to note is that if K is a special alternating link, then any minimal genus Seifert surface for K is a definite surface, which just follows from an argument with the signature and the genus, right? So they're all definite surfaces. So furthermore, we can find some minimal genus Seifert surface that avoids the boundary of the disk. So this is really a deep result. This is coming from sutured manifold theory. This is kind of like one of the main results of sutured manifold theory, and was used by Charlemagne and Thomson to prove the cosmetic crossing conjecture for the unknot. So, we don't know which Seifert surface it's going to be, but it'll be minimal genus, which implies that it's some definite surface. Now, as long as the crossing arc does not separate the surface, the previous argument works, right? And then we can also argue that the determinant can't switch signs because the surface still has to be positive definite, so it should have a, the details are maybe escaping me, but you can use that fact for that issue. It's a good question. So as long as it doesn't separate the surface, we're fine, right? But what if it does? What if it does separate the surface? Well, if it separates the surface, then it lifts. We can think about the lift of this crossing arc to the branch double cover. And this cut-off chunk of the surface gives us a null homology for this lift. And here we're gonna use another tool, which was used by Lidman and Moore, and this is what they used in their result, which is that if the branch double cover is an L space, and the crossing arc lifts to something null homologous, then the crossing change is nugatory. So what's under the hood here is the surgery characterization of the null homologous unknot in L spaces due to Gainelin. So you can argue that a cosmetic crossing change downstairs gives you a cosmetic surgery upstairs. And as long as we know that that knot is null homologous, we can conclude that it's an unknot, which tells us that maybe a bit too much details there. But under the hood, at this point, we are applying some Higard floor theory to this result. So that gives us that piece of the puzzle. When we put those together, we can conclude that a special alternating knot does not emit a non-nugatory cosmetic crossing change. So that's proof of theorem 1. So I have a little bit of time. Let's see what we have. So I won't say much about the proof of theorem 2, but I kind of want to give the motivation for it, right? We can take a different perspective on this, and we can ask what's really being obstructed here. And it's quite easy to note that if the determinant of K plus is equal to the determinant of K minus, where here this is before and after the crossing change, if we think about the two-component link from resolving this crossing change, then that determinant should be 0, right? And this is actually that submatrix we were talking about earlier is really the Gordon-Litherland pairing for that two-component link, right? And we use the fact that that has non-zero determinant. But we can say something a little bit stronger. So more generally, we can say that if the Alexander polynomial of K plus equals the Alexander polynomial of K minus, then that two-component link has 0 Alexander polynomial. Right? And this is kind of really what's being obstructed here, right? So rather than trying to obstruct a cosmetic crossing change, we can try to obstruct a non-trivial band move to a two-component link that has 0 Alexander polynomial, right? Because any cosmetic crossing change will give you such a band move, where by a band move I mean we're cutting the surface to get a two-component link, right? So we can just kind of try to obstruct this. And if you kind of push this and you look at the Alexander module, you can check out the paper, but it's kind of the motivation for this argument. And that's where this Fox-Milner condition is coming from, because knots that are sliced, they will tend to have these band moves, right? So it makes sense that there's this connection between this problem and thinking about concordance, right? And I think it's an interesting question to ask that if a knot admits a cosmetic crossing change, can we say anything about its four-ball genus then? But I have not been able to say anything about that. All right, some additional results. As an application of the argument for theorem 1, we have this other kind of nice result that if a link has a branch double cover in L space, And then the first homology group has a kind of a maximal size minimal generating set, which is a confusing thing to say. And then it does not admit cosmetic crossing changes, so that, I don't want to talk about this, but that pretzel knot is an example. And then this is coming directly out of theorem 2. So applying theorem 2, we can prove the cosmetic crossing conjecture for this infinite family of knots, which I've cooked up specifically to not be handled by any of the other numerous obstructions to cosmetic crossing changes. There's a lot of things you can do. That's one particular 4-parameter family of pretzel knots that you can prove this for. I also want to just mention that this conjecture is open for all but I think 4 knots with 10 crossings or fewer. So, you know, and it's also on knot info, exactly which knots this is not known for. So you can go on there, you can kind of pick your favorite knot. It was previously 5. We were able to knock out one of those knots. So, you know, that's nice. Let's see. Can we do it for all alternating knots? I actually think this is the wrong question, which I'm out of time, but you can ask me. I actually think positive knots are maybe the right knots to think about, and it's not obvious from the name, but special alternating knots are actually exactly the knots which are both alternating and positive. So I think that is maybe a better class of knots to think about. And you know, a question that kind of comes up naturally here is, can you do a crossing change on an alternating knot and preserve the determinant? Which is, this argument almost shows that this can't happen, but it doesn't quite show. I think this is an interesting question, even regardless of the cosmetic crossing conjecture. And there you go. 18 alternating knots with 11 crossings is the count there. But thanks for watching. Oh, what an excellent question. Well, right, I mean, one thing is this connection with concordance. We know that if a knot is positive, then the 4 genus is equal to the 3 genus, right? So you can obstruct band moves in a certain way in that sense. And you also know, right, we should be able to say something about minimal genus surfaces of positive knots, right? Are they quasi-positive? This is not known, but there is a result which is due to somebody I am forgetting now, that any essential Seifert surface of a positive knot, I want to say Miyazawa, but that might be wrong. Any essential Seifert surface of a positive knot is free. So it's, it has the complement is a handle body, right? So you actually, if you want to use a similar surface argument, you have more control for a positive knot in a way that could be helpful for this conjecture. You know, it's a free surface, and you know that it can't get simpler in 4 dimensions. But Ian Montague and I have been trying to work on it, but not solved it yet. Yeah. Any other questions?